Hello everyone, my name is Danny. Today, I will introduce my individual project proposal titled Mask-Aware Object Removal Using Image Inpainting. The subtitle of this project is A Small Image Editing Tool with Mask Type Analysis. The main idea of this project is to build a small image editing workflow for object removal. The user provides an input image and a mask that marks the unwanted region. Then, an image inpainting method is used to complete the missing area and generate an edited result. The focus of this project is not to train a new large model from scratch. Instead, I will use existing image inpainting methods as baselines and analyze how different mask designs affect the quality of object removal.
Object removal is a common image editing task in both professional photography and consumer editing applications. For example, users may want to remove pedestrians, cars, distracting background objects, text, wires, or watermarks from an image. These examples are related to aesthetic cleanup, utility editing, and content completion. However, object removal is not only about deleting an unwanted object. After an object is removed, the image will contain a missing region. This missing region must be filled in a visually plausible way so that the edited image still looks natural. That is why image inpainting is important. Image inpainting aims to complete missing or masked regions while preserving the structure and visual consistency of the original image. In this project, I want to study this object removal process and analyze how different masks influence the final inpainting result.
The goal of this project is to build a complete but small object removal workflow. The first part is the workflow. The system starts from an input image and a user-defined mask. Then, an image inpainting method is applied to generate the edited result. Finally, the original image, the mask, and the output image are compared. The second part is analysis. The primary goal is to evaluate how mask design affects inpainting quality. In particular, I will focus on mask size and mask shape. The third part is evaluation. I will conduct a controlled comparison using existing baseline methods instead of training a new model from scratch. This scope is important because this is an individual project. Therefore, the project should be technically controllable, time controllable, and still have a clear research focus.
Image inpainting has developed through several stages. The first stage is patch-based methods. A representative example is PatchMatch, proposed in 2009. The key idea is to search and copy similar patches from known image regions to fill missing regions. The second stage is deep learning-based methods. A representative example is gated convolution, proposed in 2019. This method learns to complete free-form masked regions through dynamic gating. The third stage is diffusion-based methods. A representative example is Repaint, proposed in 2022. It uses pre-trained diffusion models and conditions the generation process on known image regions. The focus of this project is to bridge these techniques into a comparative mask-aware analysis for object removal. Instead of only showing successful results, I want to understand how different mask conditions affect the result and when image inpainting may fail.
The first related work is PatchMatch, a randomized correspondence algorithm for structural image editing, proposed by Barnes and colleagues in 2009. PatchMatch represents a traditional patch-based image editing approach. The core idea is to use randomized search to find nearest neighbor patches in the known regions of an image. These similar patches can then be used to fill the missing region. This approach is effective for texture-heavy backgrounds, such as grass, brick walls, repeated patterns, or other regions where similar patches can be found. However, PatchMatch also has limitations. It may struggle with complex semantic structures, such as faces, specific objects, text, or regions that require high-level understanding. In this project, PatchMatch is mainly used as a traditional background method. It helps explain how earlier image editing systems handled missing regions before deep learning and diffusion-based approaches became common.
The second related work is Freeform Image Inpainting with Gated Convolution, proposed by you and colleagues at ICCV 2019. This method is highly related to my project because it is designed for free-form masks. In object removal, masks are often irregular and user-drawn. They are not always clean rectangles. For example, a user may draw a mask around a person, a car, a wire, or a piece of text. A key problem in image inpainting is that vanilla convolution treats all pixels as equally valid. However, in an inpainting task, known pixels and masked pixels should not be treated in the same way. Known pixels contain valid image information. Masked pixels are missing or uncertain. Gated convolution addresses this issue by learning a dynamic feature selection mechanism. It allows the model to learn which spatial features are reliable during inpainting. For this reason, gated convolution is the primary candidate for the main baseline in this project.
The third related work is Repaint, inpainting using denoising diffusion probabilistic models, proposed by Lugmeyer and colleagues in 2022. Repaint is a diffusion-based image inpainting method. It uses a pre-trained unconditional DDPM as a generative prior. Instead of training a new inpainting specific model from scratch, Repaint modifies the reverse diffusion process using known image context. The process can be understood as starting from noise and gradually denoising the image. During this process, the known regions from the input image guide the generation, so the final result remains consistent with the original image. Repaint is attractive because it can handle arbitrary or even extreme mask shapes. However, diffusion-based inference can be slower and may require more setup time. Therefore, in this project, Repaint will be treated as an optional comparison method rather than the required baseline.
After reviewing these three methods, I will not implement all of them equally. PatchMatch is fast and intuitive, but it has weak semantic understanding. Therefore, it will mainly serve as background. Gated convolution is suitable for free-form masks, which matches the main focus of this project. Since object removal masks are often irregular and user-defined, gated convolution is the most relevant main baseline candidate. Repaint has a strong generative prior and can handle difficult mask conditions. However, because it may have slower inference and more setup cost, I will keep it as an optional comparison. The strategy is to first build one robust baseline, most likely based on gated convolution or a similar available implementation. After that, the main focus will be comparative mask analysis. This keeps the project feasible for an individual project while still giving it a clear research direction.
The proposed workflow contains 5 main steps. First, input selection. The user selects a target image for editing. Second, mask creation. The user defines a binary removal region. This mask indicates the object or area that should be removed. Third, inpainting. The system applies a baseline method, such as gated convolution, to complete the masked region. Fourth, generation. The system produces the edited image result. Fifth, comparison. The result is compared with the original image and the mask, so that we can analyze the quality of the inpainting result. The implementation priority is divided into 3 levels. The must-have part is baseline implementation and comparison. The should-have part is mask type analysis. The optional extras include repaint comparison and a simple Gradio or web-based user interface.
For the experiment design, I will use an experiment matrix. The first factor is mask size. I will compare small, medium, and large masks. The second factor is mask shape. I will compare square, thin, and irregular masks. The third factor is scene type. I will test natural scenes, indoor scenes, and text-related scenes. The fourth factor is failure cases. I will observe difficult examples, such as faces and geometric lines. There are also several risks in this project. The first risk is high training cost. To reduce this risk, I will use pre-trained weights and avoid training a large model from scratch. The second risk is slow inference. To control this, I will focus on gated convolution first and keep repaint as optional.
The third risk is unstable user interface development. Therefore, I will prioritize a script or notebook workflow first. The fourth risk is bad visual results. If some results fail, I will document them as failure cases and analyze why they fail. In this way, even imperfect results can still contribute to the final discussion.
The expected results of this project include three main deliverables. The first deliverable is an object removal tool workflow. The second deliverable is a comprehensive comparison report. This report will compare results under different mask sizes, mask shapes, and scene types. The third deliverable is failure case analysis documentation. This will help explain the limitations of image inpainting methods. The expected contribution is not a new image inpainting model. Instead, the contribution is a controlled analysis that provides insights into how mask design directly influences inpainting quality. This project is technically feasible because it uses existing methods and pre-trained models. It is also research-oriented because it focuses on controlled comparison and failure case analysis. In conclusion, this project provides a feasible and research-oriented exploration of modern image manipulation through mask-aware object removal.
This slide lists the main references used in this proposal. The first reference is PatchMatch by Barnes & colleagues, published in ACM Transactions on Graphics and SIGGRAPH 2009. The second reference is Freeform Image Inpainting with Gated Convolution by Yu and colleagues, published at ICCV 2019. The third reference is Repaint by Lugmeyer and colleagues, published at CVPR 2022. The fourth reference is the course material for the presentation and term project guidelines. These references support the research background, method selection, and experiment design of this proposal.
The references used in this proposal are listed here. Thank you for your attention. I am happy to answer any questions.